record feature.
Okay.
And after we finish our session, you'll have an icon on your desktop that will look like a flower. And the next time you go to log in to join GoToMeeting, you just have to double click on that. In other words, you don't ever have to go back and re-download it.
All right.
Okay? Now, at this point, the best way to proceed is for you to, if you can, verbalize some of the problems that you've been given that you want to do, some of the algebra problems.
All right, so we're working on properties of radicals,
Okay.
like squares and that fun stuff.
Okay. Do you have a specific problem? Yeah, go ahead.
All right, the first problem is 24, the square root of 24.
And you're supposed to simplify that?
Yes.
Okay. Let's talk about radical properties. If I have the radical of the product of two things, A times B, that's the same thing as radical A, radical B.
All right.
If I had the square root of A divided by B, that's the same thing as square root of A divided by square root of B.
Okay.
So our goal with the square root of 24 is to turn it into two factors where one of them is a perfect square, like this.
Okay.
And then this I can turn into 2. So square root of 24 becomes 2 root 6.
Okay.
Okay? And that's the name of the game whenever you're simplifying these, is to find factors of whatever this number is. And let me give you another one.
Okay.
So we're looking for factors of 200, two numbers that multiply to give you 200, where one of them is a perfect square.
Okay.
Well, first of all, let me back up a second. Let's go through all your perfect square numbers. What's next?
16.
Keep going.
That's as far as we went in class.
There's 5 squared.
Okay.
There's 6 squared. There's 7 squared. There's 8 squared. There's 9 squared.
Okay.
There's 10 squared.
All right.
Okay? So when I give you this problem, you're looking for factors of 200 where one of them is a perfect square number. Well, what would that be?
100.
Yeah, that's the biggest one. And that's always the one you want, is the biggest one you can find. So this turns into that, correct?
Yeah.
And this I can convert to an integer. That is 10. So that's how you would do that one. Okay? Now, let's take another one. Let's take square root of 10. Well, the only factors of 10 that aren't 10 and 1 are 5 and 2. So I could certainly write that way, but that's not a simplification. That's 2 terms instead of 1. And I cannot pull a whole number out of either one of these things. Therefore, the simplified is same thing, square root of 10. In other words, unless you can find a factor of this number that is one of these perfect square numbers, there's no simplifying it.
So it's a no solution?
No, it's not a no solution. It just means that is square root of 10. That's its final simplification. It doesn't go down further.
Okay.
Let's take another one. Square root of 80. What would that be?
Wait.
let's say that the only factors you can figure out are 4 and 20.
Yeah.
That's okay. In other words, it'll work regardless. Well, what's the square root of 4?
2.
But square root of 20 is actually square root of 4 times square root of 5, right?
Yeah.
So I can bring another 2 out. So I have 2 times 2. So square root of 80 is actually 4 times square root of 5. Now, it took me 2 steps to get there because I didn't realize that 16 is also a factor of 80. In other words, had I realized that I could write this as square root of 16 times square root of 5, now in one step, I've got it narrowed down. Same answer, but I got there a little quicker because I was able to find a bigger factor than 4 right off the get-go. So it's not absolutely necessary that you find a factor that is the biggest perfect square. You'll eventually get to the final answer, but it makes it quicker if you spot the biggest perfect square. Let's go back and talk about square root of 200 again. Well, you spotted that that was 100 times 2. But what if I didn't see that? What if I saw that it's 4 times 50? Okay, well, that's okay. That's 2 root 50. But then root 50 is root 25 times root 2. And root 25 is 5. So 5 times 2, that would be 10 root 2. In other words, I still get to the correct answer, even though I didn't do it the most efficient way possible.
Yeah.
I had to do it in multiple steps. Whereas when you did it, you spotted right off the get-go that it was 100 times 2, and that becomes 10 immediately, so you immediately get to this answer.
Yeah.
That's the secret of radicals, is just breaking, is factoring, really. Do you have some others?
Yeah. So the first 2 are basically what we were just talking about, and then it starts getting into the square root of 49x3, like x to the 3rd power.
Like this. Okay.
Yes.
Separate your numbers from your variables, first of all.
Okay.
In other words, I know I can write this way, right?
Yeah.
Well, what's square root of 49?
7.
Okay. And then I can write this as the square root of x squared times the square root of x, right?
Yeah.
In other words, x to the 3rd is equal to x squared times x to the 1, adding the exponents. So that's why I can write the square root of x cubed as the square root of x squared times the square root of x.
Okay.
What's the square root of x squared?
X.
Yeah, so this now becomes this. And this is your answer.
Okay.
So it's the same process, even though there's a variable in it. Still breaking it down into where you can take out, I was able to pull out a full x because the square root of x squared is x. I wasn't able to do anything more with that. That has to stay square root of x.
Okay.
Okay? All right. What else you got?
So after a similar problem like that, it starts getting into fractions.
Okay.
So like 23 over 9 square root.
So break this into 2 fractions.
So that, I don't know.
Square root of 23 over the square root of 9.
Okay.
Okay? Which one of those can you simplify?
9.
Becomes,
3.
there's your answer. Now, I can't simplify that anymore. One of the reasons is that's a prime number, so it doesn't have any factors other than 23 and 1.
Okay.
So the moment you spot a prime number, you know you're done in terms of reducing it.
Okay.
And this is your final answer, the root 23 over 3.
Alright. So then after that, it's kind of a similar problem, except it's negative square root 17 over 100.
Like that?
Yes.
Okay. Break it down.
So square root of negative square root 17 over square root of 100.
Which one of those turns into a number?
100, so that would be 10.
And the minus sign doesn't go anywhere.
And 17 over 10. That's the answer. Alright. So then
What does this equal? What does this equal to?
Negative 2.
No. You cannot take the square root of a negative number.
So it's no solution?
Well, correct. At this point in algebra, it's no solution. Once you get pre-calculus, you'll learn about imaginary numbers. And this is actually equal to 2i, where I is equal to the square root of negative 1. Even though I just said that you can't take the square root of negative numbers, they've made up a number, an imaginary number, that is actually the square root of negative 1. But it's only used for higher math purposes.
Yeah.
At lower levels of math, like algebra and stuff, they just tell you you can't take the square root of negative numbers. So when you gave me this problem, I knew the negative sign was outside of the radical. Had to be.
Okay.
They wouldn't give it to you otherwise.
Alright, so then another problem would be square root 36 over z squared.
Separated into two fractions.
So square root of 36 over square root of z squared.
What do both of those turn into?
36 turns into 6 over z. Okay.
Okay. Now, before we go any further, let's talk about one thing that they may or may not have taught you.
Okay.
But that is, if you have a problem like this, where you have a radical in the bottom that doesn't convert to an integer, this is an irrational number.
Okay.
If I were to try to write that as a decimal, it would be never ending. It starts 1.71 and then goes on like pi forever. Okay?
Yeah.
Well, there's a convention in mathematics that says you never want an irrational number in your denominator. So if I had this and I had to give it as an answer, I wouldn't be able to give it like this. Well, any fraction can be multiplied by the number 1. This case, I'm going to multiply this by the number 1, only 1 is going to be that.
Okay.
What happens when I multiply that by the number 1? Well, the top turns into this. And the bottom, what's square root of 3 times square root of 3?
9.
It's actually just 3.
Okay.
Okay? In other words, it turns into the square root of 9, which is 3. Okay? So it would not be correct to give that as an answer, but it would be correct to give this as an answer, and they are the same number. It's just this one has been rationalized so that I don't have the irrational number in the denominator. Notice that it's in the numerator now. And that's what you frequently have to do, is you have to move the irrational number to the numerator. So, have they taught you this yet?
Yeah, there's a problem on here like that.
Okay, so what would this be?
It would just be 1 square root of 2 over 2. for the
Right,
answer.
you're right. It is square root of 2 over 2, but how I get there is by multiplying this by the number 1, and the number 1 that I'm going to use is square root of 2 over square root of 2.
Yeah.
Well, if I multiply numerators, I get square root of 2. If I multiply denominators, I get square root of 4, which is 2. So this is the same as that, only it's in proper form.
Okay.
Okay? All right, what else do you have?
So, and then they start getting into more complex problems like 3 square root 25c to the 7th power d to the 3rd power and over 64. And the number on the outside is a square root, so it's 3 square root, like 3 to the 3rd power for the outside.
All right. Before we do this problem, let's talk about how we handle these variables.
Okay.
In other words, how would I take the square root of z to the 7th?
So you'd have to break that up so
To what?
to the like the 5th maybe or 6th over times z.
Now, what is that equal to?
Z to the 6th power.
The square root of z to the 6th power
Okay.
is what?
Z.
Z to the 3rd.
Yeah.
Notice why. When I take z to the 3rd and I multiply it by z to the 3rd, I get z to the 6th by adding the exponents.
Okay.
So, and when you're taking the square root of something, what you're saying is, what two numbers multiply together to give me z to the 6th? The two same numbers, well, z to the 3rd times z to the 3rd gives you z to the 6th. So I can take this z to the 6th now, and taking the square root of that becomes z to the 3rd. Well, I still have this square root of z, so that's the answer for z to the 7th. The square root of z to the 7th.
But how do you know to get z to the 6th power?
Well, let's do a couple more and you'll figure it out.
Okay.
This is equal to z to the 8th times z to the 1st. What's the square root of z to the 8th?
4.
Z to the 4th. It's half of this exponent.
Okay.
So this answer would be right there. Z to the 4th times the square root of z is the same as the square root of z to the 9th. So when you have a variable and you're doing square roots, you basically want to split this thing into an even number and whatever's left over. In other words, if this was z to the 13th, I'd want to split it up into the highest even number is z to the 12th times z to the 1st, and then the z to the 12th becomes z to the 6th. The square root of this becomes z to the 6th times the square root of z. So that's basically the way you handle all variables.
Okay.
Okay? So let's go back to this problem you gave me.
Alright.
Give it to me again. I didn't write it quite.
So it was the 3rd power and then...
You meant this.
Yeah.
Okay? That's the 3rd root, or the cube root. And let's talk about that for a second. If I say the cube root of 8, that's the same thing as saying 8 to the 1/3 power. It's also saying what number multiplies together 3 times to give me 8.
2.
Exactly. 2 times 2 times 2 is 8. Therefore, the cube root of 8 is 2. And this is the same as that in terms of notation. Okay? So, what was inside the radical?
25c to the 7th.
C or Z?
C, like cat. And d to the 3rd next. Yeah. Over 64.
Okay. So, let's break all of these down. So in the numerator, we're going to have the cube root of 25 times the cube root of c to the 7th times the cube root of d to the 3rd. In the bottom, we're going to have the cube root of 64. Okay? Well, the cube root of 25 is not reducible.
Yeah.
There's no factors of 25 that have perfect cube numbers in them. So that stays like that. However, the cube root of c to the 7th can be written as the cube root of c to the 6th times the cube root of c, right? What would the cube root of c to the 6th be? What number?
3.
Well, it's c squared.
Oh, yeah. So
Notice that c squared times c squared times c squared is c to the 6th.
yeah.
Therefore, the cube root of c to the 6th is c squared.
Okay.
Okay? So, I'm going to replace this with c squared. So now I have the cube root of 25 times c squared. Well, what's the cube root of c? Just stays the cube root of c. Can't reduce it. But the denominator, what's the cube root of 64? It's a whole number. It's a small whole number.
Isn't it not 8?
It's 4.
Yeah.
4 times 4 times 4 is 64. Therefore, 4 is the answer. Okay, now, I'm not quite done because I want to put this back together with this because they're both cube roots. So the numerator would still have this c squared, but then it would be cube root of 25c, and then in the denominator it's 4. So everything reduces to that.
Well, what happens to the
Oh,
d
excuse
to
me. I forgot the d. What's the cube root of d cubed?
d?
Right there. And it's all by itself. No cube root on it anymore.
Okay.
Okay? In other words, I took out everything I could from the numerator. I took out a c squared. I took out a d. And that's all I could take out. The whole point of these things is to take out everything you can from inside the radical and put it as a whole integer if you can, or a variable without the radical sign.
Alright, and then...
Hold on, before we go on, make sure you understand cube roots of stuff. What is the cube root of x to the 9th?
So that would be x to the 3rd.
Yes.
Okay.
Because x to the 3rd times x to the 3rd times x to the 3rd equals x to the 9th. So depending on whether this is square root or cube root or 4th root, depends on how you handle this. Have you had to deal with 4th roots yet?
No, he's only gone up to
Square roots. In other words, when you write the radical sign without a number, it presumes a 2. And if you're talking cube root, you put the 3 right there. And you pronounce it cube root, not 3 times radical x to the 9.
Okay.
Okay? All right. So what other problems do you have?
So then we have a problem that is, let's see, it's 8 over 1 plus 3 to the second over 3 squared.
Over the cube root
No, just squared. So
of 3?
yes.
Okay. So, what's the problem with this expression? Why do we need to simplify it? What is wrong with it now?
So we can get the square root out of the denominator position?
Right. In other words, right now it has an irrational denominator. That's not allowed. So the way we get rid of the square root in the denominator is multiplying it by the conjugate. The conjugate being this. Just the same two things, only with a different sign in between. Okay? Now, since I want to multiply the denominator by the conjugate, I got to multiply the numerator by the conjugate also. Because once again, I can only multiply this fraction by the number 1. And that, what I have circled, is the number 1.
Yeah.
Okay? What's going to happen is it's going to get rid of the radical sign in the bottom. When I take 1 plus, let's do the bottom first. How do you multiply these two together?
Combine like terms?
What do you call it?
Like combining like terms? Is that...
Well, did they teach you something called FOIL?
Yeah.
When you're multiplying a binomial term by a binomial term, you want to FOIL it.
Okay.
So the first things you multiply together are the first two terms. That's 1.
And
Then 1 times this negative root 3, that's a negative root 3. And then this 1 times this positive root 3, which is a positive root 3. And then finally this plus root 3 times this minus root 3, which is minus 3. Well, these two cancel each other, and you end up with 1 minus 3 or minus 2. So the denominator turns into minus 2. That's a rational number. That's what we wanted, was we wanted to turn it into a rational number. And the numerator is all I have to do is multiply 8 by both of these terms. So it's 8 minus 8 root 3. So there would be an acceptable answer, except I haven't simplified it. I can divide top and bottom by the number 2, which turns it into 4 minus 4 root 3 all over negative 1. And this negative 1 becomes 4 root 3 minus 4. There's your answer. Let's talk about that for a second. If I have a minus b, it's always equal to the negative of b minus a. Right? In other words, take this over here and distribute that negative sign. What do you get? You get minus b plus a. Well, that's the same thing as that. Okay? So we had in this problem, we had a negative 1 in the bottom. Okay, well, I can first of all take that negative 1 and put it out in front, as long as I put parentheses around it. So there's my answer, but I can now simplify it by distributing that negative sign. Well, that becomes minus 4, and then the negative times a negative turns into a plus 4 root 3, and this becomes 4 root 3 minus 4. So that's how I got that answer, starting with this answer. In other words, I reversed the two terms because of the negative sign.
So
Another
what if it was
example.
a positive?
Let me give you an example. 2 minus 5 is the same thing as minus 5 minus 2. Notice that 2 minus 5 is minus 3. Notice that 5 minus 2 is 3. With the minus sign, that's also minus 3. So this principle is very valuable to know. This principle that x minus y equals the negative of y minus x, no matter what y and x are.
Okay.
Okay?
I see that.
And we used it on that last problem in order to simplify it down as much as we could. We used that principle. Okay, you got another one?
And then it's getting into 5 over 3, like, to the third power.
Is it to the third power or the cube root?
Cube root 32.
Of 32?
Yeah.
Okay. I can do two things here. I'm not sure how they've taught you how to do this. First of all, let's deal with it straight away. In other words,
Okay.
let's write this differently. Let's write it as 5 over 32 to the 1/3 power. The cube root of 32 is the same as 32 to the 1/3 power.
Okay.
The problem is it's an irrational number, and I've got it in the denominator. So what could I multiply that by to turn it into a whole number? How about 32 to the 2/3 power?
Okay.
Notice that when I add the exponents, I'm going to end up with 32 to the 1.
Yeah.
Okay, well, I multiply the bottom by 32 to the 2/3. I got to multiply the top by 32 to the 2/3. But I've accomplished my goal because now what I get is 5 times 32 to the 2/3 all over, well, the bottom becomes just 32. So there's your answer, and there's more to do on that. I can still simplify it a little bit. But just to illustrate how you get a cube root out of the denominator, it's by multiplying it by the same number raised to the 2/3 power instead of the 1/3. Okay? Now, let's go back a moment and let's talk about the cube root of 32 because that's not simplified. In other words, if the task was just to simplify this, well, I want to break 32 up into what? I want to break it up into a perfect cube and whatever else is left.
Okay.
8 is a perfect cube. Right? What's the cube root of 8?
2.
So this cube root of 32 becomes 2 times the cube root of 4.
Okay.
Now, I could do that first. I could change that into 2 cube root of 4, and then I'd only have to work with this cube root of 4 in order to rationalize it. I said there were two different ways we could do that, and I did it this way just to illustrate a point. However, it's worth knowing what this means. What does this mean? It means the cube root of 32 squared. That's what it means right there.
Okay.
In other words, when you have a fractional exponent, this is the root, that's the exponent.
Okay.
So what would 8 to the 2/3 be equal to? Always do the root first. Do the cube root of 8, which is
2.
and then square 2.
So that's 4 over
Just 4.
4. Yeah.
The answer is 4. Because what it really is it's the cube root of 8 is 2, but then we still need to apply this 2. 2 squared is 4. Okay, let me give you another one. What's 27 to the 2/3?
That would be 9.
Good. That's what fractional exponents are all about.
Okay.
Okay, now let's go back and look at this problem one more time, and let's do it a different way. We're going to get the same answer, but we're going to do it a little bit simpler, or probably a little bit more easy to understand. Well, I know that it's 5 over cube root of 8 times cube root of 4, which is 5 over 2 cube root of 4. Well, now how do I rationalize the bottom? If I rewrite this, I get 5 over 2 times 4 to the 1/3 power. What do I have to multiply the bottom to get rid of that irrational 4 to the 1/3?
The 2.
About 4 to the 2/3.
Okay.
In other words, if I multiply this bottom by 4 to the 2/3, I'm going to get rid of the irrational part of it. Well, I have to multiply the top by the same thing. In other words, I can still only multiply a fraction by the number 1. There's my number 1. And now the top becomes 5 times 4 to the 2/3. And the bottom, well, this times this is just 4. Times 2 is 8. So there's my actual answer. And it's the same as my other answer. It's just the other answer had 32 to the 2/3, and I hadn't simplified it yet. In this case, I simplified it before I started instead of waiting till the end.
Okay.
And the net difference was actually significant because instead of having to multiply everything by 32 to the 2/3, I was able to multiply everything by 4 to the 2/3. So simplifying it first has its advantages. Got another one? We'll do that first.
Alright. So then it's getting into 3 square root 2 minus square root of 6 plus 10 square root 2.
Okay. How can I write square root of 6?
3.
It's the square root of 3 times the square root of 2.
Okay.
Okay? And I'm writing it that way, not because I'm simplifying it, but I'm trying to turn everything into apples. I can't do anything with square root of 2 minus square root of 6. This is an apple, this is an orange. So I can't combine them. But once I turn this into the square root of 3 times the square root of 2, notice what I'm looking at now. I got a bunch of apples. I got 3 apples minus square root of 3 apples plus 10 apples. I can factor out a square root of 2 from each of these terms, leaving behind 3 minus square root of 3 plus 10, or 13 minus square root of 3. So this whole thing turns into this. Only because you want to convert everything to the same thing. Let's do another one. Let me make one up. What's this? It's an apple and an orange.
Yeah.
But what that is one apple plus one orange. There's no way to combine it.
Yeah.
What's this? Now I got all apples. I got 2 apples and 1 apple. How many apples do I have?
3.
And the apple is square root of 2.
Okay.
Okay? If I had this, what's that equal to?
4.
I got 3 oranges and 4 oranges. How many oranges do I have?
7.
And the orange is square root of 5.
Okay.
Okay, you got another problem? Hold on, let me go back and do one more, just so you're clear. Let's do this one. Square root of 3 plus square root of 12. Can I add those two together?
No.
Not at the moment. But what if I change square root of 12 into and then the square root of 4 becomes a 2, which I'll put in front like that. Now I can add them together. What do I get?
Then it would be 5.
No, I got 1. There's an implied 1 in front of here.
So it would be 3.
Yeah, 3 root 3. So sometimes when they're different numbers, you can add them together if you can turn one into something that looks like the other. In other words, I was able to take my root 12 and turn it into 2 root 3's. Well, now I got 2 root 3's and 1 root 3 gives me 3 root 3's. In other words, I turned my oranges into apples. My 1 orange was equal to 2 apples. And now I got 1 apple plus 2 apples, and I can add them together.
Okay, I see.
Okay? And the problem that you just gave me was that. Well, that's an apple and an orange, but I can turn this orange into root 2 times root 3. And now I've got a root 2 there and a root 2 there, and I can add them together.
Okay.
All right, what else do you got? These are relatively hard.
Yeah, they're not.
I'm
easy.
surprised you're getting them in Algebra 1. Are you in an honors Algebra 1 class?
No, I'm just in a regular algebra.
Regular? Okay. And this is what they're on at this point in the year. Okay, I guess that's probably correct. I don't have very many.
Yeah,
I don't have very many Algebra 1 students, so I don't know quite what the curriculum is. What else?
Now they changed the curriculum a lot. Alright, so then there are problems where it's a cube root instead of just a regular square root.
Okay.
So 4 cube root 5x.
4 cube root of what?
5x
Okay.
minus 11 cube root 5x.
What's our apple?
4. 4 and 11.
No.
5x.
The cube root of 5x. There's our apple right there.
Mm-hmm.
So if I have 4 apples minus 11 apples, what do I have?
-7.
Apples, which are cube root of 5x.
Okay.
So as long as stuff is the same, just do regular, in other words, this problem is basically the same as 4x minus 11x minus 7x. Why can I combine those? Because they're x's. They're both apples. So you can combine stuff as long as it's the same. If it's different, you can't combine them, or you have to change it so that it is the same. Partly the same, at least. What else?
And then it's getting into stuff like parentheses. So it's square root 3, parenthesis 8, square root 2, plus 7.
Inside the parentheses?
Yeah, square root 32.
Okay. Right off the get-go, we can see that we have a problem here. How do I add 8 square roots of 2 to 7 square roots of 32? Well, let's change that, because I can end up with a square root of 2 over there.
Mm-hmm.
Let's take that 7 root 32 and simplify it. What are factors of 32?
I don't remember what that is. 16, 2.
Okay, now what can I do?
Simplify 16.
Well, what's the square root of 16?
4.
So I'll replace that with a 4. Now I got 7 times 4 is 28 root 2.
Okay.
So 7 root 32 is the same as 28 root 2. So I can just replace that with 28 root 2. And now notice that I've got 8 root 2 plus 28 root 2. Those are both apples. I can add those together. What do I get?
28, 36, and 2. Okay.
Okay, in other words, I got 8 apples plus 28 apples. That's 36 apples. Okay, now I can multiply this times this.
To get 6.
Right, so 36 root 6 is the answer.
Okay.
And I can't simplify the root 6 anymore. I mean, I could make it say root 3 times root 2, but that's 2 terms instead of 1, so that's not really a simplification. In other words, you only simplify if you can pull a whole number out of there. I was able to pull a whole number out of that because it factored into 16 times 2, and that's a whole number, 4. But if I had, say, 34 instead of 32, well, now that's square root of 17 times square root of 2. Neither one of those is a perfect square. I can't pull a whole number out of it, so I would never simplify. That's simplified, square root of 34. I would not break it up into these two things because there's no reason to. I can't pull a whole number out. You only break it up if you can pull a whole number out.
Okay.
Okay? All right, what else you got?
So, let's see. There is a problem that I'm a little bit confused about.
Okay.
So, it's 12 over 2 to the second power, sorry. But,
What's in the denominator?
2 squared, sorry, 2 squared plus 7 squared.
Like that?
No,
Square root.
I always forget, yeah, root, sorry. I always forget that they're roots.
So the square root of 2 plus the square root of 7?
Yeah.
Like that?
Yes.
Okay. Again, we have an irrational denominator that it
Yeah.
doesn't look like we can do much with. But if I multiply this thing by its conjugate, now you know what I mean by conjugate?
Yeah.
In other words, the conjugate of a plus b is a minus b.
Yeah.
That's what a conjugate is. Well, when I multiply these two irrational numbers by the conjugate, I get 2 minus 7. I get minus 5 in the denominator if you FOIL them.
Okay.
Okay? So whenever you multiply by the conjugate, you're going to convert an irrational number to a rational number. Now, I still have to multiply the numerator by that, same thing. So now the new numerator, I got to multiply 12 by both of those. So I get 12 root 2 minus 12 root 7. Cannot simplify that at all.
Okay.
Well, I could take the minus and reverse these if I wanted. I could take the minus out. Let me just make sure you understand what I mean by that. In other words, that answer that I have circled is the same as this answer.
Okay.
I've reversed the order in the numerator, and I've removed the negative sign from the denominator because I reversed the order in the numerator. So this is a little bit prettier answer than what I have circled. They're both the same number. It's just the bottom one has fewer minus signs in it.
Okay.
Whether your teacher needs you to do that last step or not, I don't know. She may be perfectly happy with this as an answer. She may want this as an answer. I'm guessing she's probably going to be happy with that.
Probably.
I wouldn't think that yet that she wants you to go all the way to that last step.
Okay.
Like I said, if you put that in a calculator, you'll get the same number as if you put this in a calculator.
Okay. So there's one more problem that I'm looking at and kind of weird. So it's parentheses 2 root squared over 5. Root squared 5.
I'll tell you what. Let's do something real quick while I've got you on the phone. Do you have a smartphone with a camera on it?
I do.
Take a picture of what your paper says right now. Hold it about a foot above it. Make sure that it fills the screen and you have good light. Use the flash if you have to. Take a picture. And then do you know how to send that picture to my email?
Yeah.
Here's my email.
Okay.
Let's get you so you know how to do this, because there's going to be sessions in the future where you're going to have difficulty verbalizing. And when you have difficulty verbalizing, anybody would have difficulty verbalizing it. The best thing to do is to take a picture of it and send it to my email.
Okay.
Go ahead and do that. And then the next time you need to send a picture to my email, you type in DA and it'll give you my whole email there. The first time you'll have to type it out fully. If you don't know how to send it, ask somebody and they can probably help you. But at some point you'll want to know how to take a picture and send it to my email.
Okay, I got it to send.
Okay.
So.
Let me pull up my email and see if I got it yet. Yeah, no, not yet. I didn't. Did you add the 1949?
Yes, I did.
And davidcowan1949
Yep.
Not getting it.
I can try again.
Try again. You might have just mistyped it or misspelled it. Make sure that everything's spelled. It's COWAN and 1949. There it is. I just got it.
Okay.
Just came in late, that's all. Okay. So I can pull that up on my screen where we're both looking at it, and that'll make it a little easier for you in that you won't have to verbalize stuff. But there's actually, you learn a lot by being forced to verbalize it.
Yeah.
In other words, you learn how to pronounce this stuff because you probably never get a chance in class to stand up and say what this problem is. So you don't get any practice at verbalizing stuff. So there is a bit of a benefit to verbalizing stuff, but sometimes you're going to have like graphs that need to be interpreted, and you can't verbalize those. So on problems like that, you'll need to take a picture and send it to me.
Yeah.
Problems like this, we could certainly verbalize it. What was the last problem? Was it this bottom one?
Yeah, the very, very last one.
Okay, well, let's do that one before we finish up here. Squared means 2 root 5 minus 4 times 2 root 5 minus 4, right?
Yeah.
FOIL it. First is that times that. What do you get?
4.
4 times 5.
Yeah.
In other words, you got to multiply the 2 times the 2, and you got to multiply root 5 times root 5. Root 5 times root 5 is 5. 2 times 2 is 4. So that first term is 20.
Okay.
Next term is this first term times the outside. In other words, FOIL is the O means the outsides. So minus 4 times 2 root 5 is minus 8 root 5.
Okay.
And then I want to do the insides. The I of FOIL is the insides times one another. So minus 4 times this is another minus 8 root 5. And finally, the L of FOIL stands for the last. That would be minus 4 times minus 4, which is plus 16. Now I can combine all my like terms. Well, that's a like term with that, so that's 36. And I got minus 8 apples and minus another 8 apples. That's minus 16 root 5. There's your answer.
Okay.
You good to go, Kendall?
Yeah. Yeah, I am.
Okay. Well, congratulations. You had a pretty good first online session, and I think you probably have figured out how it works online. Now, I've recorded this, so I'll stop the recording.